This is the workshop for video talk through part 5. So we are now on step 10. We have detrended our time series and we've produced plots of the power spectrum for both our raw and detrended time series. We can see those up here in figure 2 and figure 3. Now step 10 says try and use the P-Welch method or P-Welch function for computing the spectrum from the function that was generated in workshop 3. Now don't use necessarily that function. I mean, you can use it, but you'd have to be careful to have things in the right order. And I suggest that you use the function that I have supplied for you here. So that's in your workshop 4 files directory. So let's just open that up. Okay, so this is basically the same as the one that was generated in workshop 3, but there might be some differences in perhaps how some of the variables were defined. I've taken out the plotting, text at the bottom, plotting commands at the bottom, and I've added in some more information about what the input and output do. Okay, so we want to plot the power spectrum for both the raw and the detrended time series. So what I suggest we do is we actually edit this plot PSD CO2 script, and rather than calling the find PSD FFT function, we call the find PSD P-Welch function instead, and using the same inputs. So I'm going to overwrite this, but I'm going to save this one as plot PSD CO2 P-Welch, and we're going to change a few things in here. So let's change the FFT to P-Welch. In the comment we should change this as well actually, so change that to P-Welch. Change the title to underscore P-Welch. Okay, and what else do we need to do? Using P-Welch method. And down here using P-Welch method. And anything else we need to change? Yes, the function call as well. So I'll write that as P-Welch here. Okay, and because I don't know what the axes are going to be, I'm actually just going to remove these and use the default, whatever MATLAB decides is the best fit axes limits for the time being. And I think we'll put these in different figures. I mean, if you want, you can use different subplots to display it how you like. So of course figure 4 and figure 5. And save that. We'll just have a quick look inside the PSD P-Welch function. So we've got the same inputs into the P-Welch function that we used in workshop 3. So we're defining our sampling frequency, which is 1 over the sampling interval, the length of our time series n. We'll go with, quite arbitrarily, choosing a segment length of 5, which means actually the segment length is going to be extremely short because this time series is very short. It's only 161 data points long, so, or 160 data points long, because we're only we're chopping off the last number. So this means that actually we're going to have fairly coarse resolution unless we put in a higher FFT number. Now the ones that I've generated in for the workshop display here have used a higher FFT number, but I think it's a bit misleading to use that, so because you can see it's smoothed out quite a lot of the variability, and it suggests that it's got higher resolution than it actually has. So we're going to use the length of the Fourier transform, NFFT, is equal to the window length, NW. Okay, so we just put those inputs in. Now, MATLAB will actually take the time series on its own, and it will have default values for each of these. So you don't actually need to input. You don't need to change anything here. I thought it was just instructive because we've had a look at what the windowing does on its own. That it might be instructive just to be able to play with these different variables and give it to you in a format where you can make changes and just see how it changes the output. Okay, so that's the p-welch function there. So if we go back to our plot PSD CO2 p-welch script, and that's saved so we can run it. Okay, so it's generated now another two figures, okay, which we can compare. So what's happened? Actually, we should swap these around. Okay. So if we compare the raw time series using the Fourier transform method, that's figure 2, with the raw time series using the p-welch method, then you can see that the p-welch method has smoothed out everything. Actually, you don't see any spectral peaks where we'd expect to see them at all. It doesn't look like there's any periodic component except something perhaps down at very low frequencies, which, as we know, is not necessarily a periodic component. It's a trend. It's the linear trend that we try to remove. And what we can see in the detrended time series, the top plot in figure 3 here uses the fast Fourier transform method, and in figure 5 at the bottom we can see we've got the output from p-welch method. So effectively what has happened is that by detrending the time series, we've removed, in both methods, we've removed this low energy, low frequency energy. Okay, so it's missing in both of these detrended power spectra. And we still see that there is a peak here at once per month. Okay, so that's where our peak frequency is occurring. Now the axes limits are different here. Okay, so we can't necessarily compare peak values, but you'll see that there's a lot more variance in the Fourier transform method of the power spectrum from the detrended data. There's a lot more variability. But that's at the expense of resolution. So we have, by dividing the time series up into lots of segments and averaging those power spectrum from each of the windowed segments, then we have helped to reduce some of the noise, but we have lost some resolution here. So that is effectively the problem with using Welch's method or any sort of averaging method, is that you do lose frequency resolution, so it looks quite coarse. The data points are more further spaced apart in the p-welch method output. Okay, so for the coursework, it suggests you just change nseg from 5 to 3, and I'm not quite sure which. If I have a look at the p-welch function here, okay, I updated it on the DLE, but if I try changing nseg to 3 in here, then what happens is that it returns a non-integer number here. So again, it ends up creating a problem. So what I did was if you put in the function floor, if you floor a number, it basically just removes the decimal points. Okay, so I can put that in where I think there might be an issue. So if we change nseg to 3 here now, it should make any issues, but I have updated that on the DLE so you can download that one rather than the first version I put up. But that was only an issue for the first workshop, so anybody who was in the Thursday workshops, you would have had this function anyway. Okay, I hope that's okay. So that brings us to the end of workshop 4.